What if I told you a perfect copy of a brain is now running inside a simulation, acting on its own with no AI guiding it and no one training it? Scientists have just done something that sounds like science fiction. They Control-C'd and Control-V'd a brain into a digital body and put it inside a virtual world. Now, it's not a human brain. It's something smaller, with far fewer brain cells. But that's not the point here. Because for the first time, we're not just studying intelligence, we're starting to build it. Ancient stories predicted that humans would go from powerless to capable of creating and shaping the world around us. Mythology tells of a titan who stole fire from the gods to awaken humanity, only to face a cruel, unrelenting punishment that trapped him in his own body. Is this the first ever simulated mind? Does it think it's alive? And is the human brain next? And maybe the most uncomfortable question of them all, if a mind can exist inside a simulation, how would it ever know? Join me as we unravel all this and much more and enter the Codex Legendarium. I'm Shelby Melanson. Imagine for a second what it looks like to perfectly map every building, avenue, back alley in a major city, like Manhattan or Tokyo. And I'm talking everything, all the way down to potholes and the divots in the tar, the glowing white figures of walk signs at crosswalks, every last bit of text on every street sign, plus every single wire carrying everything from electricity to internet data, and what that data is and where it's going. If you could do that, you'd have a perfectly precise 3D map of the entire architecture of that city, down to the finest detail. Now imagine doing that for a brain. It's called a connectome, and we're not talking about the fuzzy images that come out of MRI machines here. No. Imagine mapping a brain neuron by neuron, synapse by synapse, to create a perfect blueprint. Now imagine copy-pasting that blueprint into a computer simulation and giving the brain a digital body, like the one that it has in the real world. What would happen? Well, that's exactly what scientists at a company called Eon Systems endeavored to find out. They mapped the brain, hooked it up to a simulation via an open-sourced advanced physics engine called MuJoCo, which is specifically designed to run simulations for robotics and biomechanics, by the way, and gave it a physics-simulated body, complete with 87 individual joints called the NeuroMechFly V2. Then they applied gravity, friction, and other movement constraints to mirror real life. And when they tried it, the creature, lo and behold, started acting exactly like you'd expect its real-life version to act. Walking, grooming, feeding itself, completely on its own. Fully autonomous, with no training, AI, or other software in sight. The whole premise of AI is that in order for a system to be intelligent, the intelligence has to be trained into the system. But this showed that the intelligence was already baked into the system's architecture, in other words, the brain's architecture, and that it can be transferred out of the brain. Let that sink in. Okay, here's what happened. Okay, so step one, map the brain. To do that, take a brain, preserve it so it doesn't degrade, then slice it into ultra-thin sections, around 30 to 40 nanometers thick. That's 1 to 2,000 times thinner than a strand of your hair. Then use an electron microscope to image every last detail of every slice. Stitch all of that information together in the proper order, and boom, a 3D computer rendering of the brain. From there, just figure out which synapses go with which neurons, add in that information, and get some humans to proofread it all, and then you have a connectome, an entire wiring diagram of a living brain. So, a simple task. Not. Here's the thing. A human brain is fairly large as far as brains go. It's thought to have roughly 86 billion neurons, or brain cells, and 100 trillion synapses, the microscopic gaps between neurons where cells can send signals to communicate. So, the folks over at Eon thought that it might be best to start small. Something with a brain roughly the size of a poppy seed or a grain of sand, with around 139,000 neurons instead of 86 billion, and 54 million synapses. They landed on a tiny creature often used in bioscience studies called the Drosophila melanogaster, the fruit fly. So, they mapped the fly's brain, and using a kind of AI called machine learning, they created a 3D digital reconstruction. Worth noting, algorithms make mistakes. So they actually formed an organization called Flywire Consortium and built an online platform for hundreds of volunteers to help check the algorithms' work. The group says that without the extra help, it would have taken one single person 33 years to manually check all of this information. Before we get to what happened when the brain map was dropped into its virtual body inside a digital simulation, let's get a quick recap on how this kind of brain mapping started and why it started. The first ever Connectome was mapped back in 1986. The creature of choice was a species of nematode whose entire body is only about 1 millimeter long. It has a brain-like central nervous system with just 302 neurons and 5,000 synapses, all of which were charted and then hand-drawn with colored pencil to showcase what portions controlled what. Since then, scientists have done the same thing for other worms, various kinds of larvae, and most recently, mice. Or at least a 1 cubic millimeter square of mouse brain tissue. Yeah. If you're curious, the tissue came from the primary visual cortex and the retina, aka the areas that process visual information and help the mouse to interpret what it actually sees. From that, you get a visually striking model that, to me, looks a whole lot like an interconnected system of trees in a vast forest. Scientists went as far as launching the human Connectome program in 2009, which attempted to map the brain via high-resolution MRI scanning and a whole bunch of other advanced techniques. But it concluded in 2016 and did not come anywhere close to the precision of the fly. Yet, there's still one huge question here. Why go to all the trouble? Human nature has always sought to understand itself. So it almost goes without saying that while these studies have started small, the ultimate goal is to be able to do this with a human brain, to figure out exactly how our minds tick and why we're able to do, feel, and be aware of all of it, and what separates us from other life forms. In the medical sphere, neuroscientists say that connectomes might one day shed light on brain diseases, or on brains that are wired a little bit differently, like people with autism or ADHD, all the way to disorders like schizophrenia. In other words, the whole banner of neurodivergent. But there's another reason having intimate knowledge of the brain's structure might be of use, according to the scientists. Enter something called neuromorphic computing. Basically, it's an approach to creating computer hardware that mimics the human brain, its synapse structure, and how it processes and carries information. And thanks to that, these systems are extremely energy efficient, just like the brain, adaptable, just like the brain through neuroplasticity, and capable of what's called parallel processing, which essentially means they can perform a ton of different tasks all at once at the same time. I went through a full breakdown on all of this in my episode on organoids learning to play the video game Doom, so if you missed that one, go check it out. Anyway, neuromorphic computing traces back to the 1980s. Fast forward to today, and tech giants are actively developing them. Intel's Hala Point is currently the world's largest and most advanced neuromorphic system, packed with a whopping 1.15 billion neurons and 128 billion synapses. Though another project might soon be gunning for that title. Back in 2023, researchers at Australia's International Centre for Neuromorphic Systems announced that they were working on something called Project Deep South, a neuromorphic computer capable of 228 trillion synapse-based operations per second. I know. Not much news on it since then, but we'll see. Now, mimicking the structure of something is one thing, right? But what about the actual one-to-one reconstruction, the fly-brain connectome? Now, on the ethics side, we'd be here for 100 years if we were to get into the what is consciousness and who has it debate. The short version is that some argue creatures without complex brain structures, including insects, aka fruit flies, aren't conscious in the way that we are and don't have inner lives. Several studies from the past decade, including one from 2024 signed by dozens of scientists, by the way, says there is a, quote, realistic possibility for elements of consciousness in reptiles, insects, and fish. And given that, it is irresponsible to ignore that possibility in decisions affecting that animal. One of the scientists who signed onto the declaration says they are, quote, taking the topic seriously, not dismissing it out of hand as a crazy idea in the way that they might have in the past. Back to the digital side, if the architecture of this fly brain is perfectly replicated, preserved in a digital space, if the same synapses are firing, at what point does it go from being a model to being a functional mind in its own right, to something that doesn't just simulate, but experiences? The point here is, we don't know, and we probably won't know, considering we can't even decide if things that are inarguably alive in the way that we know life to exist are conscious, let alone something in the digital realm. However, there is one thing that kept coming up in my mind over and over while I was researching for this video. The idea of a brain in a vat isn't a new one. Pop culture has been making use of this trope for decades, and while most of them describe a physical brain in a jar, a digital copy-paste of a brain housed inside of a digital body, inside a simulation seems pretty accurate of a comparison to me. Especially since in some of them, like The Matrix, physical ones are fed simulations anyway and believe that they're in the real world. Interesting parallel, isn't it? The same idea shows up in one of my personal favorite book series from when I was a kid called Maximum Ride. In Book 4, The Final Warning, we meet a character and the book's main antagonist called the Uber Director, who, and I quote, who was little more than a human head attached by means of an artificial spinal column to a series of plexiglass boxes. Mechanical means allowed this character to talk, but he was so trapped inside his body that he couldn't even nod his head and had to send eye movement signals instead. As for thinking, he's described as sending a thought signal to the nanoprocessors implanted in his brain. Likewise, Season 2, Episode 7 of Fallout, the post-apocalyptic TV series based on the video games of the same name, depicts a former US congresswoman who used to stand against corruption and corporate influence. But in the show's present day of the year 2296, her head is found preserved and wired to a computer's mainframe, used to power mind control technology. She's found begging for, essentially, the end of her life to stop the torture. In the 1995 French fantasy film The City of Lost Children, Irvin is a talking brain in a jar, literally. He's one of the only characters in the entire film with a moral compass and symbolizes loneliness and the desire for human connection, which he can't have. He also suffers from bad migraines. All in all, you basically see two categories of brains in jars: the villains and the good ones who are trapped, suffering, and want out. Now, is that because it makes for entertaining script writing, or is it a hint about something more? Here's the thing. There's one story that, if you ask me, embodies this discussion better than any other: Prometheus. You know the one, the titan from Greek mythology that shaped humans out of clay. But when Zeus, king of the gods, denied humans the gift of fire, Prometheus basically said, forget that, because in his mind, he wanted to free humanity. So he stole fire from Mount Olympus, hid it in a fennel stalk, and gave it to mankind. Because of it, humans developed civilization, medicine, agriculture, metalworking, architecture. You get the idea. The story, and more specifically, the fire, is most often used as a metaphor for knowledge and scientific development. But it was more than that. Prometheus gave something divine to human beings that weren't meant to have it: the power to transform reality. Before fire, humans were powerless. After gaining fire, they became creators in their own right. Beings that could shape the world around them, almost godlike. Think about it. Scientists today are doing something a lot more extreme than just stealing fire. They're going from using intelligence to trying to manufacture it. And if you can simulate a mind, you're going way beyond just using it as a tool. Now, this is where the story and its parallel to our discussion today gets interesting. Prometheus did not get off scot-free in this story. As punishment for his actions, Zeus had him chained to a rock at the top of a mountain. And every day, a vulture would come and eat his liver while he was still alive and chained there. And thanks to his immortality, his body would regenerate, so he was essentially forced to endure this suffering endlessly. Prometheus was not punished because fire is evil. He was punished for disrupting the boundary between gods and mortals. And in the myth, the punishment for that is eternal suffering that's specifically tied to the body. Chained, unable to escape, forced to endure a repeating cycle. Now think about the potential for a digital brain inside a simulation. In theory, it could potentially exist inside a controlled, inescapable loop. No body, no agency, no escape. Like the movie Groundhog Day, but without the happy ending. So what if we're repeating the exact same story, but without knowing what the punishment is for it yet? Now, full disclosure, experts who have or are working on fly connectomes were quick to chime in about this online, pointing out that there is still a lot of missing information from these connectomes, plus elements of the brain that we don't really understand. Some also made the point that a full mouse connectome is a long ways off in terms of money, time, and understanding, and that there's a lot more to recreating a brain than just blind copy-pasting. That said, the tagline for Eon Systems, the company behind this fly connectome again, is literally, and I quote, "Upload the human mind." So even if we are a ways away from the mouse connectome, and even if it is just designed to be eye-catching and generate hype, that logo, it seems like the goal here to make the jump to human connectomes is clear. And also, on the point of being far away money and time-wise, back in 1965, the co-founder of Intel predicted something that later came to become known as Moore's Law, that the number of transistors in a single microchip would double every year for the next decade. Basically, that technological growth is exponential, and in 60 years, we've gone from a dozen transistors on a chip to tens of billions. In other words, tech today is yesterday's stuff of dreams. So just food for thought on the timeline of all this. All in all, we set out a long time ago to understand the brain. And in doing so, we may have taken the first step towards actually recreating it. What we're building now isn't exactly a brain in a vat, but it might be the first step towards one. And if a mind can exist inside a simulation, the boundary that once separated creator from creation kind of begins to collapse. At this point, the question may no longer be what can we build, but what we could be trapping inside of it. But what do you think? Is this the first mind successfully copy-pasted into a computer? Can a mind truly be detached from nature? And what's the difference between reality and constructed experience? I would love to hear your thoughts about this in the comments, and if you have an idea for something you'd like to see a future episode on, let me know. And of course, if you enjoyed this deep dive into mysteries, myths, culture, and science, please take a second to like and share this video, and if you want to see more, subscribe. It really, really helps get the word out there. Until next time, stay curious. Thank you.